Okay, it will be about the spaces. If you remember last lesson, we finished seeing the rotating cube illuminated using some sort of basic Lambert reflection. But the reflection was wrong, because the light seems to rotate along with the cube. The same thing that may happen if you, for example, have a sort of selfie stick attached to the figure. The object rotates, so does the light source illuminating it. But that's not the effect that we want to achieve. We want that the light source remains still in the space of the 3D world we are representing, and only the object rotates. So we have seen that the computation of light involves information about the normals, the light position and direction depending on the type of light source. We will see some different types of light sources, like for example directional light, which is the most simple, a light that only have a direction, point lights, lights that have only a position in the space and illuminates starting from that point 360 degrees around them, and spotlights. Spotlights have both a position, both a direction. And also we have the observer, which is the camera usually, which has some sort of position inside the 3D world and a direction of looking. Usually what happens? Normals and vertex position are usually expressed in terms of local coordinates. There is a pivot point of the model, and all the vertex and normals are expressed as relative to this pivot point, which is the center of the 3D world in which the object is represented. But usually lights and the observer are expressed in the world coordinates. I have some object, any number of objects, and I want to put those objects inside a bigger world in which they can be represented all together in different positions. Then I usually put some lights inside this world in order to illuminate the object that I put inside the world. But then I have two different coordinate systems for different objects. I have the local coordinate system used for the object to express their vertices and normals. And then I have the world coordinate used usually to express the position of the camera, the position of the light, and in which I put each single object. That's why we experienced a wrong light effect. We will see more about this. The light seems rotating along with the rotation of the cube. This is because in our latest vertex shader, we will see the code in some moment, the vertices are transformed using the world view projection matrix, but the normals are not. So the normals remain expressed in local coordinates, while everything else changes world, changes coordinate system. Thus the graphical representation is correct, because we put it in the right world, but normals doesn't follow this transformation. You see, normals are just interpolated. The exact same normal that I receive in input is sent to the next step of the shader, while instead positions are transformed using the world view projection matrix. So, if we want to achieve the intended light result, the data about normals, light, and eye position must be expressed using the same coordinate system or space. So we have to decide in which space we want to be working in. We will see the following ones: word space, camera space, object, and static spaces. Each one presents some advantage, but also some disadvantage. Some are easier to understand, others less. Let's say the issue here is that a lot of mathematical transformation applied to the matrices, multiplication, etc., are all performed in the client code, not in the shaders, in the server code. So this means basically that this wants to give you an idea that the client and the server code are not separated. That's why we prefer in the course to use both, even if the focus of the course is on the GLSL part, so the server part of the language. That part of the language cannot exist without a coupling part of the client code. In this case, many of the operations that determine in which word we are operating are performed inside the client code. Mind that that's not mandatory. It is possible to move some of those operations inside the shaders operation, but that depends on the specific program that you are writing. So there is the local space, there is the word space, there is the view space, and those three spaces are those that are more commonly used to move as the reference word for the visualization. So let's start with the word space. Word space, let's say that it is the easier to understand. Simply, we move everything inside the same coordinate system that we use for the whole 3D world. This means that position and normals of the objects must be moved inside the word space. This is done usually. Here you have let's call it summary. So we usually have those values: vertex position, vertex normals, light direction, position, and eye position. Usually they are expressed, and you have vertex position are usually in local space, as does normals. So they must be transformed in word space because they are not in that same space. Light direction, position, and eye position instead are usually expressed in word space, so we don't have to transform them, which is a sort of advantage. So we, in this case, need to send 3 matrices to the vertex shader, not just the word view projection as we does in the latest example. Of course we need it, otherwise we don't see anything projected in a 3D world. But we also need 1 matrix to transform only the vertex position, and 1 matrix that will be used to transform only the normals. The position of vertices is assigned to the fragment shader because we need them to have information about the surface when we need to compute the light bounces. We use the position of vertices for 2 purposes. In the vertex shader, of course, vertex position is used to paint, to draw the surface. But then we need those information, and not in the word view projection coordinate system. But we need them for computing light bounces in the word spaces, in the coordinate space that we have decided to use for whole our pipeline. So, not considering the word view projection, which is used only for projecting in a 3D world vertices and having a 3D view of them, we need one extra matrix to transform the vertices and then have information about the surface for light computation purposes, and also for the normals, for having the right direction. The advantage here is that light direction, light position, and eye position can be passed to the shaders without any modification. When this is something good, when we have many lights, for example. If we have many lights, not having to transform them in one space, from one space to another, avoid us matricial multiplication. We don't have to transform the light direction, light position, and eye position, so we don't have to multiply them, and we save in operation. So, about the transformation and exactly which kind of operation are required in order to move values, data from one space to another, we will continue in a while. I want to show you the wrong example that we, with a little modification. Here you have basically exactly the same code we have seen as our last example, last lesson. There's one difference that I will highlight in a while, a couple. If you remember last time we had an issue, the dark part, instead of being dark, were completely white. And that's the first difference between the last example. And the second one is that instead of having one cube, we have 4 cubes. And that's to highlight the behavior of it. So, about the first, the problem with the white. Maybe I can find the last lesson example to be more specific. It was this one, exactly this one, the last example. And you see that instead of having something dark, where the light doesn't hit the surface, we have some white part. That's simply an alpha problem. Problem is just an issue with the OpenGL. By default, the alpha channel is on, so everything that is not perfectly 100% painted with one full color, but have some, let's say, shade less, is considered to be blending with the alpha channel. And in this case, it goes to the bottom level of the windowing system, which is white. That's why it is mixing with white color, because there is no, we didn't specify any color for the farther background layer, so it takes the white and it mixed with the white. It is enough that in the code you disable the alpha channel and that error is solved. So here we have inside the drawing.js you see, when we declare the context, we set as a flag that we don't want the alpha channel. So that mixing with a color that we don't want to have is off, and the color respects what we want to have. Another thing that I want to highlight, because it's quite important, is this. If you see, we still have just one vertex buffer object, meaning that we have specified and sent as a data pack only the vertex of one cube. But during the rendering process, it is possible simply by changing the word matrix of that cube to replicate the cube many times. So the code is exactly the one that we have seen as the last example, last lesson. The only difference is that we declare, instead of just one word matrix for the cube, we define many, with different values, of course. In this way, we take objects from local coordinates that are exactly the same, but by multiplying with the word matrix, we put them in different places of the whole 3D world that we are creating. We just have 3 here, because the 4th is animated. If you remember, we were able to animate the cube, rotating and scaling it a bit, only because we didn't modify the real vertex position. We just modified the word matrix used to multiply, to move the object from its local space to the world space. And by performing this modification, we obtain the animation effect. And if you see, in the animate function, which is called each rendering cycle, we changed, with the values used, the cube matrix of only the 3rd cube. During the drawing call, in the compute matrix, when we allow the view matrix, so the camera, to move inside the space, we update information about all the cubes. And now, in our draw scene, instead of calling all the uniform passing once, we did the same thing 4 times, and each time exactly the same parameters are passed, except the projection matrix. Projection matrix, we don't have, of course, having 4 different word matrices. We need 4 different projection matrices because we have to compute the projection of each object inside the scene. So we pass a different projection matrix for all the elements inside the scene. In this way, it was possible to save memory, because another way for doing the same thing was to load 4 different cubes, for example, and having 4 vertex buffer objects and then painting them. But that was not performative, because you can simply have the data about your shape once and then use as many times as you want, creating instances of it. So we start working on starting from this example that you can download in the website, BIP website, if you want to try to code along. And we will add some Blinn reflection to the material in order to see the highlights of the reflection color along the material. And see, it can be a little bit boring if you want, but we try to exactly do the same thing, the correct same thing, in the 4 different spaces. I will save you from the static space because it's pretty simple as from a coding perspective, but the other are quite important. I want to say that this part will have also it can be drastically different, the client code, not that much the server code. So the JavaScript will be different for the 3 example. The GLSL not so different, but with significant differences too. And the sense of all of this is that we don't yet know in which way this part will be asked at the exam. But since at the exam there is at least one big question about GLSL, and that question is all usually has been up to the past year about writing a shader's code or correcting a wrong shader's code. It is important that you know that the shader can behave very differently depending in which, let's say, a shader's code that is correct for camera space is totally wrong if instead the client is sending information in world space. That's why this part is important. You cannot avoid having the coding of the shader absolutely coupled with the main program code that sends data. That's what this lesson is all about. So, okay. This is a note. Usually, when you have to transform a position, as a rule of thumb, that's not always like that, there are a lot of exceptions, but usually when you have to modify a position from one word to the other word, you simply multiply the vector holding the position for the matrix that describes that word. So for example, if I have to move the vertex position from local space to world space, it is enough that I multiply the vertex position for the word matrix. In that way, I change the word for it. For the direction, usually it is the word matrix only if there are no scale modification to the object. If there are scale modification to the object, we have to take the 3x3 submatrix of the word matrix, invert and then transpose it in order to achieve the intended result. Okay. What is assumed usually about the word space is that it is usually expensive, but is the most easy to understand logically with respect of the other one. Okay, so first thing, we try to correct the normal Lambert reflection that is wrong in the past example, and then we add the specular part of the color as in a Blinn, as per Blinn shader model, to see why it is important to modify, to have the position of the surface and the correct implementation of a light shader. Back to the code. Okay, we have it here. If you have question in the meanwhile. Okay. So, since we only have to correct the normals in the fourth cube, we will just create, instead of an array, just a single variable to hold the cube normal matrix. And since we have a cube normal matrix and we have to send this cube normal matrix to the shader, we also need an handle for it. We can call it normal matrix handle. Of course, we now need to take the normal matrix from the shader. Since it is a uniform, we can simply take it from here and we call it N matrix, for example. Okay. So we have the position where to send it, but we have to create it. Okay. This can be done in the animation function, I think. Yes, in the animate function. Okay. So after this one, and we need, since we do have scale modification, we need to perform the transpose and inversion of the word matrix, which is defined here. So utils invert matrix is of course a function that inside utils perform the inversion of the matrix. Transpose matrix is pretty self-explanatory. We take the object word matrix, and now we have the normal matrix that we need to transform the normals of the cube. At this point, we have in the rendering cycle to send the right uniform, the right matrix. So let's find a suitable place. So let's say projection matrix is here, so exactly after that, but we need to do that only for the latest one. So if the index of the element that is currently being rendered is less than 3, we pass as a matrix into normal matrix. Just check that it is correct. It is correct. Without any need for normalizing it, the cube normal matrix, because we don't need, as I told you before, not the projection but the word matrix, cube word matrix of I. Oh no. Okay. So since the 3 static cubes are not experiencing any scale modification, we can just pass simply the object word matrix to modify also the direction of normals. But since the 4th object does have a scale modification, we cannot do the same thing, and instead we have to pass this cube normal matrix that we created. So I can copy the line because the position is the same, but I have to take this one. Oh, yes, I did a mistake. So, wrong copy. It was not the handle that must be modified, but of course it was the matrix itself to require modification. So. Yeah. Okay. So this is what we have done. We transformed the normals from the local space to the world space in order to be coherent with the light specifications. Since light were specified in world coordinate, we have to specify in the same coordinate system the normals too. And since it is possible to transform the normals using the world matrix if there are no scale modifiers, for the 3 static cubes we use it. Instead, because for the 4th cube there are scale transformations, we have to resort to this cube normal matrix, which is the transpose inversion of it. the 3x3 submatrix will be computed inside the shaders code because it is easier. Next step is then to modify, of course, the shaders code. So we go to the shaders code, fragment and vertex, and now we have one more uniform here, which is the N matrix, the matrix that we used, we just created and we want to use for the normals. And of course, we have to do this. But this will generate an error, because in normal is a vec3, while N matrix is a mat4. Those are the kind of mistakes you can find inside the code. By simply creating on fly a mat3 out of a matrix 4, we obtain the 3x3 submatrix from it, and this operation is perfectly legit. I don't think we need any modification to the fragment shader. Fragment shader simply taking input the normal as the vertex shader wants to send it to. Okay, let me check in which folder am I now. Now you see that the faces of cube changes in color depending on which of its faces stands in front of the direction of the light source. If you remember, from this perspective on a scene, we will rarely see any black faces, except for some extreme position, but you see that the faces are changing color. That's because now everything is in the right space. Okay. This one is one of the trickiest arguments in this part and the practical part of the course, so don't hesitate if you have questions, because I understand which is not exactly easy on the first approach. So, okay. Now we want to implement the specular reflection. And the specular reflection is required by more complex, less basic, less standard illumination model. Let's say that we want to implement the Blin reflection model. Okay. For doing this, we need some extra information. First of all, if you remember the formula for the Blin reflection, you should have seen that in the theoretical part of the course, it requires, for the computation, to know the position where the light is hitting the surface. We can give this information if we pass one more matrix, which is the vertex matrix, that by modifying the vertex position provides this information. So we add this vertex matrix handle to modify the vertex position. And then, since now we have also a specular color, we need to specify specular color and the specular power. Those two are extra informations that are required by the formula. And also we need one last handle, which is the eye position handle. we also need the observer position in order to compute everything correctly. Okay. So directional light colors remain exactly it. We change the color to a simple white. We don't need any extra colors. And now the cube, the material, also required the specular color and power. Cube. Let's say that we want the specular color to be red, which is horrible, but at least you can easily spot the reflection. And the cube specular power, which will be instead just a floating number. Let's put 20, which is very big, again, just to see something. Then, put it here. Since we have an handle for it, we need the eye position, which will be, let's do it in the, let's type an array in JavaScript, which is an effort just to show you that it is possible. And it will be of 3 floating values because it is a direction, so we just need them. We don't need a scale value. So float 3 is more than enough. Okay. Yeah. Specular, yep, you're right, specular power. Thanks. Okay. So this one is going to be created. For those we have created the values that we will pass. Now the shader will be compiled and we need more matrices. One more at least, which will be vertex matrix handle. Let's check that. Okay, it's the same. And let's call it P, stand for position. It will be just a name. Okay. Then, since we have eye position, material, specular color, and material specular power, we need 3 extra values to be sent, and so more uniforms to be collected. Okay, let's go here for the material specular color. Let's copy the line. Easy. So all uniforms, so we can simply copy this, and of course we have to give them names. So eye position can be simply eye position, while for the other two we decided to have an M spec color and an M spec power. That's it. So in the compute matrix, which is here, about the animation part, we don't need to modify anything in the animation part. But during the matrix computation, we have to pass the observer position. Create it at least, and then pass it. And since the observer position is the same of the camera, we just simply pass the observer position as the values of the current camera position. Let's check. this has been done here because at each cycle the position may change, so we have to update the position that is sent to the shaders, and here we have to pass all that we created. So we just need the cube matrix, and so we can go here and copy the line, and as vertex matrix handle we need to send the cube word matrix, which will be the same for all 4 cubes, and the vertex is okay. And now simply the colors and the position. So cube light color, in the light position and light color handle, we duplicate the line. Again, there are 4 values that we are passing, so it will be cube specular color, or don't remember, but this is about the light. This will be for the material specular color. Then we need a single value, because the power is just a float, so we don't need to any extra values, and that's why we put just one F, which is exactly the same thing but sends only one value. And we have to send specular power, I don't remember how it's called, to specular power. Okay. And here we have to use the right specular color. So at the position of specular color handle we send the specular color, at the position of the power value we send it to the specular power. We just need the eye position. Eye position will be a uniform 3F because it's just the direction, so just 3F, and we will send observer position 0, 1 and 2. Okay. So observer position is defined, and also here, okay, specular power equals specular color 2. Now we have to change drastically the shaders. First of all, we need one more matrix here. We call it P matrix, and that's it. Then we also need another varying, because we are not just passing the normals, but also the position. So we need also the position. And then, since we have this, we have to define it. It will be equal, of course, to we have used a vector tree, so we have to do things like this. Basically what we need to do is this: P matrix multiplied by in position. Of course this cannot be done for many reasons, because we need a vec tree in output, and because we have a map4 here. So we can create one of the way for, we can create a vector 4 in position in the exact way we did here. So now this multiplication is correct. But we will get an error because f position is vec3, so we have to put this into parentheses and then x, y, z. Just collect the 3 elements out of that. Fs position, we don't have only the normals, but we also get the position, but that's not all. We have more uniforms that we have defined. We have a specular color, for example. We also have a specular power, and that's everything for the material. But we also have another direction, which is the I position, and then the Fs position. Okay. All those information are mandatory if we want to create the reflection. So, first of all, let's normalize the I position, which, because of many different, well, it depends. We have to normalize the I position difference Fs position. So in this way we have a vector that indicates correctly the direction from the observer to the surface. Normalize it. It's better also to normalize the light direction, but we did it somewhere probably. No, let's do it. And then the last normalization was already done previously. It is Fs normal. Okay, now things changes. A color in this way is composed by at least 2 parts. There is the diffuse part, which follows a simple Lambertian reflection, and we already computed it. But we also have the specular part, and we have to sum them together in order to obtain the final color. For doing this, we can, for example, take this line and change a little bit the name. This is the diffuse part, which take diffuse color, the light color. Then we can change this part and, for example, use a clump. Clump is a function that ignore any results that is outside a specific boundary. In this case, we just want colors from 0 to 1, otherwise they cannot be represented in RGB mode. And so we are going to clamp the dot product that we've seen the other time, dot product between the normalized light direction and the normalized normal. Okay, clamped between 0 and 1. Okay. And this should compute us the diffuse part. Then the Blin. The Blin requires the computation of the alpha vector, so let's create the alpha vector. Vector H vector, which is the normalize, and so let's call it more correctly direction. This is the I direction. Okay, and and then we can use it to compute vec4 specular, which is equal to specular color influenced by the light color influenced by power, which simply rise to a power something, and the power will of course be specular power, and the part here in here would be again a clamping, which make a lot of parentheses around. Okay, the clamping between the dot product, of course, between the normal and the half vector that we computed just now. And again, we have to clamp everything down to 0, 0, and 1, 0. Okay. Then, let's specular. Yeah, you're right. Thanks. So the dot product, okay, this closes the clamp, and I need this here. No. Okay. Between clamps that we use here. That should be. Okay. Let's see what happened. Error. Okay. Wrong parenthesis. So power is there, but so it is power. Probably it was just a space. Doesn't like the power. Okay. From the scratch, otherwise I won't. Right. Just the flow. That's the problem. Thanks. No. That was a float. Right. So power not here, but here. So there's some problem. The dot product is correct. The clamping is correct. The power seems correct. Let's see. Okay. So let's see. You should see some red shading. When the light is reflected exactly toward the observer, we have the specular highlight. So and that seems pretty correct. Of course, it's very extreme, the specular zone. It's never that high, just to show you the thing. Okay, let me just stop the recording.